Hi everyone. Let's try to do it with some fun. We're going to talk about WebAssembly. So what WebAssembly is, how does it work, or can you use it directly in production or not, and why it's probably the future of our web applications. So first things, it's male topic. It's more and more trendy, and we have to keep an eye on it. Because it's designed to be probably the future of our web apps. It's really powerful, really efficient, and it's designed to handle all our business logic in our next application. So stay ready, it will be fine. Just a quick reminder, we're all nostalgic, I guess. So in 2001, we had Prototype, Scriptaculous, Smooth Tools, old libraries. How many of you have used them in the past? Okay, you're all. 2005, jQuery. Hello, Jake. It's a brand new library, a brand new abstraction in your browser. 2010, it's the first single-page application, and we see a new kind of design with something like Backbone. And this is a big change in the way we are designing our apps, because we don't rely on the page anymore. We are just loading our assets and let them run directly inside the browser. And we have to check on the event loop on JavaScript. And it has many impacts on the way you are architecturing and designing the architecture of our apps. 2012, Angular, 2015, Virtual DOM, React, Vue.js, etc. We are now constructing some trees of components and doing some diffs to apply to the DOM to make it more efficient, more reactive, faster, because the DOM is slower by design. So it's a big change too. 2018, progressive web apps. A new magic, new power. You can install your application directly inside your mobile, your device. And 2019, your RAM, it's okay? Or do you need, like me, something like 16 gig of RAM to run your web apps right now? This is a big problem, because we need some more and more power, and we need our app to be more and more efficient. But we can't really do that with only JavaScript. So what is WebAssembly, and how does it work? The first try came with AMScripten. AMScripten is a module, a plugin, let's say a plugin, for LLVM. LLVM is a compiler, like GCC, but a modern one, not like GCC. And it can handle any type of languages and compile it to a target, a destination. AMScripten is a first try to port C and C++ code base to JavaScript. It transpile your C code or your C++ code through LLVM to a JavaScript engine. And it worked. It was really slow, but it worked. In fact, it was just something like that. So not that efficient. But it proved that we can do it. So it leads us to another experiment, which was SMJS. SMJS is a subpart of JavaScript that can be optimized to make our JavaScript faster in our web browser. This is something like machine code, something like assembly. And it is designed to improve the way you can execute JavaScript in your browser. So it is naturally the continuity of the AMScripten experiment. We have identified some parts of JavaScript that can be optimized. But it's only a subpart of JavaScript. It can be the whole JavaScript, because JavaScript has some lacks in its design that can be solved in the virtual machine itself. First one, this is the nature of JavaScript, which is event-driven. You've got an event loop, and you're just waiting for some event that coming into your loop. And your JavaScript, your virtual machine, is just running like this. So you have to handle the event in the loop. Second thing is that JavaScript is monothreaded. So if you block your loop, because you have a big treatment to do a big computation in your event loop, you just block anything, because you've got just one thread. So you freeze your UI. You can have memory leaks, because, as I said, with single-page application, we're not reloading the browser anymore. We're just putting assets in the browser, and we're attaching some events to some clicks, some loading, etc. And if you're not releasing the events correctly, you just have memory leaks. And more, the first single-page application were just, it was just a nightmare, because you had your application and your browser continuously grow its memory footprint, and then suddenly it crashed your browser, because you just have memory leaks everywhere. So you have to handle it. And it progressively moved us from front-end developers to application developers in the browser. We had to take care about memory. We had to take care about low-level interfaces like we can do with low-level languages. So we rely on some fancy tricks like next tick with some set timeout 0. Is anyone has done set timeout 0 somewhere? Yeah, you're just registering your function to execute on the next tick on the loop, and so it allows you to delay some treatment. And it's a solution to prevent some freeze on the event loop. I remember an application I made where I need to import a bunch of vCards. So there is a lot of contacts that the users can just put inside the application. And if you're just computing the whole vCards in a single loop, you just freeze your whole application, your whole interface. So I had to rely on next tick on each vCard to have it reactive enough. So we need concurrency. We need something to run applications more and more efficiently in your browser. So we use web workers. We use service workers. This is just like if you detach some part of your JavaScript in another thread, in another event loop, but you miss some part of the browser. You can't access the DOM. You can't access just a subset of the API. So it's not that efficient. It's more powerful, but it's not that enough. We need more performances. We need more power directly inside our browser. And this is where WebAssembly comes. WebAssembly is just a new language, close to a machine code instruction, so an assembly language. And it's close to native performances. In fact, this is WebAssembly code. Nice, not? This is not a language. I said a peer developer. So in fact, yeah, this is not a language. This is machine instruction. If you want a language, you've got something like this. That is just a subset of instructions. That is pretty much more not understandable, but this is more machine instructions than just bytecode. So I can't write my application like that, and nobody wants to write their application like that. So we need something more powerful. We need to compile for the web architecture. And this is the design of WebAssembly. We stack with LLVM, because GCC must die. And this is probably most of the best compiling toolchain available right now. So you can take every language that is understood by LLVM, like C, C++, Java, Shift, Swift, Objective-C, whatever you want, and put it directly inside a compiler to obtain real bytecode available to run in your WebAssembly virtual machine. Why could we do that? Just because we can. It is fun. And it is really efficient. So the most interesting part is that JS can't handle every use case. You sometimes have some part of code base that is available on your backend or your server in another language. And if you need to port it to your web browser, nobody wants to rewrite it in JavaScript. It is more efficient to just compile it to be able to run it in your browser directly. And in fact, your browser is already a virtual machine. Your web browser is just a Chrome around the running engine, but we've got progressive web apps that are installable directly in your device. We've got Electron, we've got Cordova, and so on. We are already able to run our application detached from the browser using the open web platform. We just need more power. So WebAssembly is a language. You can compile any language to WebAssembly. This is bytecode, and this is a machine instruction. You compile it through LLVM, and you load it using JavaScript. And it can be executed in the browser, but not only in the browser. So, back to basics. Is it easy? No, it is not. First, I need to explain what is a stack-based VM. You've got two kinds of VM virtual machines available to run your code. You've got stack-based VM and registered-based VMs. Registered VM got a lot of register for instruction and the state of your memory, and there's a lot of pointers. This is really fast and really efficient because this is really close to your CPU, but it's really complex to implement and to distribute. The other solution is to use a stack-based VM. A stack-based is just like pushing instruction directly inside a big stack and being able to run inside the stack. In fact, the JVM and the JavaScript just-in-time compiler itself are stack-based VM. So it was really more simple to stack with the stack-based design and to implement the WebAssembly engine in a stack-based. What does it look like? It does look like this. You've got a stack, which is just a pile, a queue of instructions. And you've got your instructions. And you have two pointers, the instruction pointers and the stack pointer. Then, first instruction, I push the value 1 in the stack. Second instruction, push the value 2. And then I move my instruction pointer to the add instruction. So I will add the content of the stack in just one element. So I will add them, which means that I will clear my stack and push a new value inside it, which is a result of the add instruction. OK? OK. Why do I explain it? Because the stack is the main point. This is the design behind the WebAssembly virtual machine. And if you understand it, you understand how WebAssembly can be efficient. This is because if we want to realize this operation, just 1 plus 2 multiply by 3 divide by 7, I just add 1, then add 2, then add 3 and multiplication instruction, then the add instruction, because I will clear the stack each time, then I push 7, then I had the divide instruction. OK? This is like the Polish reverse notation. If you do math, this is the same thing. So this is something that I could write like this: push 1, push 2, push 3, multiply, add, push 7, divide. This is just assembly. This is exactly the same thing. Does anybody play with assembly when he was young? Oh, wow, a lot of people. OK, that's cool. OK, fun. So you understand me. I did the same with my Texas Instrument chipset when I was young. This is my first try with computer programming. It leads us to today. So, what about our logic engine and how to execute WebAssembly in our code directly? We have lots of JavaScript engine, SpiderMonkey, V8. We had Chakra because no Edge using V8 directly, so monoculture. We've got JavaScript core, and all JavaScript engines work the same way. At start, we've got the JavaScript virtual machine engine, which is an interpreter, which got a just-in-time compiler, which is able to optimize subparts of your JavaScript code if it can be predictable. So you can optimize it. And the just-in-time compiler produces machine code instruction, which is close to what WebAssembly tried to do. But those instructions are fast, but this is limited. Because to be able to run through a just-in-time compiler, your code must be really predictable. You must be able to know which type you pass to your function and which type your function will return, which is not the way JavaScript works, because this is not a typed language. So we've got a problem. And we need to optimize some part. To do that, WebAssembly uses the same engine as JavaScript. This is not two engines that runs inside your browser, because if we did that, we have the JavaScript code, we have a WebAssembly virtual machine, and if the JavaScript need to talk to the WebAssembly or the WebAssembly virtual machine need to talk to the JavaScript one, we need to make some bridge using native API written in C. So you have a first way to do call to your native API, which pass the result to the WebAssembly virtual machine, and so on. And this is just not efficient. So web browser implementers merge them into a single virtual machine. And this is the same thing that can pass directly instruction between JavaScript and WebAssembly. So it allows quick exchange. It's really fast between JavaScript calls and WebAssembly calls. It does unboxing directly inside your code. Unboxing is when you pass a value to a function, you pass the value of your variable, but you need to pass the type of your variable. And to pass it, you have to box your data inside a wrap, a box, that contains the type of your data at the current time you are calling your function. When we do that, we need to do unboxing inside your function. So the virtual machine needs to unbox the data to understand the type, and so on. WebAssembly is statically typed. So there is static type inside it. There is no need to unbox the data because the type of the data is predictable. So it's really fast. We don't need to do unboxing between JavaScript and WebAssembly. We can do monomorphic calls. Monomorphic calls is when you call your function with the same type each time for each arguments. So it can be optimized. And we can access the built-in methods directly from JavaScript to WebAssembly, part of built-in methods, but it is available. So the execution engine is able to run any kind of language that can go through LLVM and execute them directly on the web. You can write it in C, C++, whatever language you want, but you can also write them in Rust. Why Rust? Because C is good, but I got only one brain, and I don't want to divide my brain when I'm working to one part that is producing code and the other one to managing memory. I can't do that at all. So thank you, but use a modern language. There is no data race inside Rust by design, which means currently WebAssembly is mono-threaded, but when we have multiple thread and we have concurrency, we can't corrupt the data at any time because Rust handles this use case in its design. So it's really useful and really easy to work with it. It is static typed, so like WebAssembly, it is better for the rest of us. There is iterators that they are so useful. They are just awesome. This is the best iterators that I ever seen in any language. It has an excellent memory management, which is really useful when you work in your web browser because the amount of memory that can be allowed in your web browser is limited, and you have to manage it. So if you use a language that is allowed to, by design, quickly manage your memory, it's more efficient. Its community is just incredibly awesome. So really get in touch with them. They are just incredible. And it has a really good toolchain with a compiler, with some build tools, with some package tool. It is really well designed. So, simple hello world in Rust. Really, really easy. But it's just a hello world. Advantage of Rust is that it has module by design. And modules are something we really love when we are doing JavaScript, right? So it is by design inside Rust. So you don't have to deal with some wrapping, some if-is function or something like this. We had modules, we can use them directly, and they are available directly inside your JavaScript when you expose your WebAssembly code. So it is really simple to use. We have static types and iterators, so easy to do. I just add the type of my arguments and the return type of my function. I pass an enum and just act on it to simply reduce the result. And it is just returned by default in my function. This is really elegant. This is really efficient and easy to understand, I guess. And there is Cargo. Cargo is a package manager for Rust. It allows you to retrieve package, to build your code, to distribute your code, to run your code, to execute it. This is just your primary tool. And it was designed and it is developed by the people that previously did Bundler, which is a package manager for gems in Ruby. So they know their work. They know what they do, and they know their previous mistakes, and they try to not reproduce them in the Rust ecosystem. So Rust is a really good language to start with WebAssembly. And there are a lot of libraries written in Rust that allow you to increase the skills and the capacities of your WebAssembly code. So, can we use it in production right now? It depends. First, we've got the Fantastic Four. All of them embed a WebAssembly virtual machine. You can execute your WebAssembly in all modern browsers. They all work together to put it as an open standard. So it's free, it's open source, and you can use it anywhere on modern platform. So it's available right now in production. So a simple hello world for the web in Rust that will be compiled to WASM is something like this. I just write a greet function passing an argument as string and call the alert method in my web browser. I pass it a string that I want to format to include my variable in it. Okay? Right. How will it work? My timeline is the following one. First one, I need to fetch my WebAssembly bytecode inside my web browser. Yet, I don't type WebAssembly directly available in my HTML markup. It's planned. We will have it at some point. But yet, we have to load it using JavaScript and executing it using JavaScript. Yet. So JavaScript will load it inside the virtual machine, the WebAssembly virtual machine, and the virtual machine will compile it twice. First time in streaming, so you're able to start to work with your WebAssembly function even if your WebAssembly module isn't fully loaded, because the compiler starts to analyze it and to execute it. And when the whole module is loaded, then the compiler has analyzed it and it can compile it second time to optimize it in the just-in-time optimization. So it is compiled twice. Bonus point, it is kept in cache, so when you reload your page, it is faster. Then you instantiate your module. You don't have to wait. This is a premise, so you don't have to wait for the module to be completely loaded. You're allowed to work with it and to instantiate it, even if it's not fully loaded. But you instantiate it in your JavaScript, then you can access the function. So it's something like this. I fetch my module in a WebAssembly format, which is just bytecode. Then I get a result with an array buffer. I get the array buffer, then I instantiate it using in my WebAssembly virtual machine. It returns a module. Then I can access the module and access the function exposed in your WebAssembly module directly inside my JavaScript code. Boom! And it worked. If I need to transfer data between my JavaScript and the WebAssembly in my module, I just have to expose what I need to use. I use my module, I use the instance export, and then call my WebAssembly function, Rust function compiled to WebAssembly. And I pass the data, and it just worked. I've got a return result, and I can use this result directly in my JavaScript event loop. OK? Right. So WebAssembly has 4 static types available, 2 integers and 2 floats. And that's all. If you're doing math computation, this is really well. If not, we've got a problem. We've got a problem because we need more than just numbers. But a number can be really more than just a number. It can be a 8-byte element, or it can be a memory pointer. So this is the use case of linear memory. A RAM, a memory, is just a queue of boxes, and you are putting some signed integers, some bytes, inside the boxes, and you put them, and you remove them, and you move them across the boxes, and this is how a memory works, which is exactly the same thing like an array. So you can use an array in JavaScript, which are boxes, put some numbers in it, and have a pointer to point your box, your current box, like you did in a RAM, in the memory. And then you can share some part of data, binary data, between your JavaScript and your WebAssembly. How does it work? We need to first create a memory from your WebAssembly machine. You initialize it. You create a shared memory, which is just a binary array computed from the WebAssembly array buffer. You declare a pointer. You start with your variable, let's say a string. And for each character of this string, you're just converting it from its binary form and iterate over it to put them, or put the car code itself inside your shared memory from the pointer. And you've got a shared memory. This is a RAM emulation directly in your JavaScript. And you can share data between JavaScript and WebAssembly. Is that easy? No. Is that pretty useful? Yes. So we've got Wasm-bindgen. Wasm-bindgen is a library for Rust, which allow you to manage every kind of data types and data exchange and shared memory and so on directly between your JavaScript engine and your WebAssembly engine. So it's more useful and more efficient to use. In fact, Wasm-bindgen is just here to facilitate the high-level interaction between the 2 parts of the virtual machine. So how to use it? Just like that, We use the crate, which is the name for the module, the package in Rust. We use the crate Wasm-bindgen. We initialize it. There is some decorators in Rust. If you do some Python or some C++, you're probably aware of what decorators are. So this is just wrapping of some syntactic sugar around your functions. You declare the function from your web browser, from your JavaScript that you want to use inside your Rust code, and then you declare your function, like we did before, and we call directly the alert function, which is the native JavaScript one, inside our Rust code. And to load it, no more fetch, no more instantiate, no more. You just import the module exposed by the Wasm-bindgen CLI. It will generate a WASP module and a JavaScript file, which is just a wrapper to allow you to load your module and execute your module and expose your function. And you just have to use it directly in your web browser, and that's all. Way more simple than doing it by hand. Yet it just exports any JavaScript function to Rust. It exports the JS types, the boxes for boxing and unboxing data types, the cats, the getters, the setters, namespaces. And it also exposes to Rust the DOM interface, the fetch API, canvas, request animation frame, web audio, WebGL API, etc. So it's really, really useful to use. But we still need to compile it. And compiling, it's just a pain. I don't know how LLVM work. I'm not a LLVM person. I'm not a low-level language person. I'm formerly a web developer, so I don't have nothing to do with compiling. So we had a tool, which is WASP-pack. And WASP-pack allow you to simplify your workflow with WebAssembly. You just have to install some Rust binaries. It means a nightly compiler, and declare a new target, which is the WASM target. And then you just have to pack WASP-pack build your project, target for the web, your output directory, and it works. Everything will be generated, everything is ready to use, and you can directly bind your WASP-pack to your NPM account. So the package that is generated using WASP-pack is directly published on your NPM registry if you want. So you can develop any kind of libraries or WASP JavaScript modules that will be available to anyone. It's just a simple workflow tool, which is really, really, really fun. So, a little state of WebAssembly. I wanted to show you some examples that is not just a hello world example, because we can do a little bit more. Because I'm involved in some security concern, I wanted to show you something related to a blockchain. So, quick reminder, what is blockchain? A blockchain is a chain of blocks. Crypto people are smart. And each block has an ID, which is a checksum, a parent, which is a link to the checksum of the previous block in the chain, okay? A nonce, which is a random number, and an array of records, and each record is an ID, which is a checksum, and a payload. Each IDs, the block IDs or the record IDs, are the checksum of the rest of the block, or the checksum of the payload in the case of the records. Okay? It means that when you compute a block, you have a link between the checksum between the blocks, and this is what leads us to a full chain. Why a nonce? Because in the case of the Nakamoto consensus, which is used in the Bitcoin blockchain, we need to register a block in the blockchain. We need to solve a math problem. The math problem is really simple, in fact. You need to find a nonce, so a random number, which will modify the checksum of the block, and this checksum must start with an arbitrary number of leading zeros. The more complex is the consensus, the more leading zeros the checksum must have. Okay? Do I lost anyone? If I want to do that in JavaScript, it's an infinite loop. Read a nonce, a random number, and I will generate the checksum of the content of the block. So I use the parent ID, the nonce, and string representation of the records. Then I will get the result in a x value, and I will just try to find if this checksum starts with a correct number of zeros regarding to my complexity, if I want 2, 3, 4, 5, 10 zeros starting the checksum. If yes, I break the loop. Otherwise, I shuffle the nodes, I shuffle the records, because it will increase the complexity, but it will also increase the probability to get correct checksum faster. If I want to implement it in Rust, this is the same code. We've got a loop. We initialize a random number generator. We generate a nonce. We shuffle the records. We get the representation of the payload from the record. We compute the checksum. And we start to try to find it if there is a correct number of leading zeros or not. This is the same thing. This is not the whole code. You can check it in the slides repository after if you want. So, time for a demo. This is a demo day. So, crossing fingers, often it works. Okay, I let the complexity to 2 because nobody wants to wait 10 minutes to get some results of. I start the mining with JavaScript. So I try to find a nonce that will give us checksums that start with 2 leading zeros. I shuffle the records each time. It can take some time, so you can grab a coffee if you want. There is a trick for the rendering. The rendering is in a request animation frame. So I just modify with my logic code, just modify the state, which is exposed globally. And in a request animation frame, I will just check the state and update the rendering. So there is many more operations. First one. There is many more operations in the background than we see directly in the interface, because between each request animation frame, it can compute 3, 4, 5, 10 more combinations. So we've got the first one. We've got first checksum, which is the same one is the second block as a leading parent. Parent ID, so we try to find a second nonce. Coffee, anyone? Can do some dance if you want. We've got second block, and we will try to find the third one. Okay, it took 82 seconds to do it. Okay, red pill. Okay, with WebAssembly. Let's go. So this time, the interface won't be updated in real time because I was lazy enough to implement the shared memory. So it was just running in the background with Rust. And it is trying many kind of computation. It's just trying to solve the problem by itself. And I will get the result in the back when it will be ready, I guess. Demo effect. It is just compiling, but it could take some time. You know, probability. So this is just that. And we will saw the result in some time, I guess. It looks like everything is frozen because I don't update the interface. I could implement the shared memory, so everything will be updated in real time, but too complex for the demo. Oh, fuck. Not this time. Oh my God. I'm so sad. I tested it. I tested it early in the morning, and I had something like 2 minutes in JavaScript and 10 seconds with Rust. So it was just incredible. I was just, oh yeah, please, please give me the same thing during the demo. And I guess not this time. An interesting thing is that this demo is a little bit cheaty because, oh fuck, I tried. For the JavaScript part, I rely on the Web Crypto API, which is implemented in C in your browser. So it's really fast because it's native or close to native performance with the CPU. Using Rust, I can't access to the Web Crypto API. So I have to compute the checksum directly with Rust. So this is pure Rust. But this time, I guess, oh my God, everything's stuck. Fuck. Yeah, I'm sure. I'm pretty sure. You know what? Let's try to reload the frame. And or not. Everything is definitely frozen. Yeah, thank you very much. Okay, let's try again. Directly with Rust. Crossing fingers. Yeah, 6 seconds. Ah, thank you. Magic of probability. So, what's the current status of WebAssembly right now? It compiles. It can be fast, as we see. It's really lightweight because the WASM code that is produced is really small, a really small footprint. So it's really cool. We've got linear memory with typed arrays, so it's really fun. What's coming soon in WebAssembly? We've got multi-threading probably soon, which is really, really cool. It's implemented at something like 80%. So it's pretty much ready to be released in your browsers. We've got streaming compilation, untied compiler, some kind of JS module exchange, garbage collector, and they are focused on portability, runtime, etc. And we have the WebAssembly system interface that is coming. And WASI is just awesome because this is just like POSIX directly implemented in your virtual machine. So you don't need containers anymore. This is just a subset of standard interface that allow you to access files, system, devices directly in your WebAssembly code. It means that you can run WebAssembly anywhere from a unique code base for any kind of chipset, any kind of servers, farmer servers, or any type of IoT devices. It's a big promise, and last but not least, it's full open source, which Java is not. So this is really, really cool. But you have to know the web. So keep in mind, HTML DOM is for declaring your interfaces. CSS is for your layout, your styles. JavaScript is finally dedicated to your UI thread. And your background processes and background operation can be performed in WebAssembly. I don't say WebAssembly will kill JavaScript. It won't. It is not designed for that. It is just here to improve your performances of your web apps directly inside your browser or outside your browser in your virtual machine. So thank you very much. I'm Mads. I'm a tech evangelist at Always Data, which is a PaaS provider. We keep an eye on WebAssembly because it's probably a future for any of our next customers to run any kind of code and any kind of bytecode directly on our servers and our farms. So we want to be on it when it will be released. So we keep an eye on it, and you can see that this is not my natural color. So if you had any question, I think you were a little bit late, and you are probably angry, but if you want to come, get in touch, talk to me after. I'm here for the rest of the day. And I thank you very much for everything. Enjoy the rest of the conference. Thank you.